那这种时候呢，还要我们 present in parametric form 嘛，因为 x 是 free variable 嘛，我们会把它变成一个 unknown，然后写的时候 present in 这样的没有。
是没有问题，一个是这样，是没有问题的，其实是没有问题的，这样是没有问题的。就是这个U 跟 V 要合在 R 里面，就是 U 跟 V 要合在 R 里面，但是没有什么理由你要特地选不一样的 variable。
没有啊，只是看起来比较整齐这样子。因为如果没有的话，没有的话，这样写就是 x y，
就这个是 S 这个是，因为你都反正你都
对方 a b c d 啊，
没有，这正常不了。就是说 S1会 interval S3跟 S2会 interval S3 跟 S4，因为你看
x 3跟 x，
对，没有错。
左边放110啊，
什么意思？
这边
没有错，没有错。
如果放 u 跟 v 不能吗？
没有不能啊，只是说为什么要做一个多余的功？
看起来比较会乱啊，因为你 x
因为还有一个原因，你记得吗？我们有讨论过什么是 free variable。如果你这边写 S3 S4啊，也是很清楚是 free variable。因为如果你放 U 跟 V 是一个全新的 variable，但是
是我写啊，
对，没有错。
我 let，
其实这个蛮重要的，其实如果你这样子盖掉啊，这个其实有一点点问题啊。对，这两行其实蛮。
因为如果我放了之后，我又可以放进 x 而且还比较不会。
其实如果你这个放 S3 S 啊，这个东西就不要写了。如果你不要写 S2 S3 S 不用写了，其实。只是我那天写出来是为了让你知道，来我们 transform 过来的时候，这个 S3会带着一个 ES 会带着一个。
对，会的时候，
所以你，I mean 不是，就是说，like，我建议就是说你写 SIS 就好了。OK，如果你要写这种答案，你可以不用写这两行，
嗯，
然后你可以写 SIS。如果你要写这种答案，你要记得有 S 等于 SIS。
但是你比较推荐写 XIS。
对，我比较推荐写 SIS，因为这样的话会提醒你说谁是 free variable，因为看 U 跟 V 就一二三是哪一个是 free variable，就比较难看，你要亏来看这边。如果 SIS 就直接 OK，make sense。
OK，这样子。
这讲是这个 A1、A2、A3。
对，对，因为这边有写 denote the column of A by A and A3，对。
他讲 is B in 这个，然后我讲 yes，因为我找到3个 vectors，然后
你找到那个 linear combination
啊
OK
，B 的时候，他问还是
一样的问题啊。
然后可是他这里 how many vectors are in W，还是讲 infinitely solution。
对，没有错，因为你的 scalar 可以挑嘛。
所以这个我这 scalar
哦，is B in 这个只是说 B 是其中一个嘛
是其中一个。
？B 不是其中一个，不是这个是 no 嘛？因为它不是其中一个嘛，但是它是可以写成它们的 linear combination。这 A 的这个 part 是问你这个 B 有没有在这个 set 里面，就这3条是不是它其中一条？不是吗？对，这个是 no，然后这一个才是 yes，因为你说你可以解成 linear combination。
他是讲这个是 span，B 是
它的
讲它是
linear
span，
combination。对，
所以 A 不是讲不是
A 没有
问
，A 只是说在这个 set 里面有没有在这个 set 里面。
然后还有一个问题是问 span in real number power of 3那个X1、X2有那个 real number，然后如果3是 free variable 的话，它也是 span in real number 3。
我看一下你在讲什么，不是很懂的。还是我
像这种就是 in the subset of real number，
R3，
然后
这个叫 R3。
它的
对，能不能解成 linear combination？看一下，再看这样的题目。对哦，跟刚才那题一样，这个东西可以被写成他们 column 的linear combination。
如果它的 X3是 free variable 的话，还是
就有解哦，
有解，
就有解。但是是咩？你解出什么东西？
好像没有这个。
你这是 inconsistency 的问题。对，如果 free variable 的话，就 inconsistent。但是如果有 free variable，确实就是 free variable 更多解。但是有可能，没有好像不可能，好像是不可能的事情。
就是很不可能会有 free variable。
但每次的 free variable 会发生在 homogeneous。如果没有错，可以看一下，可以看一下你自己算的，好像那个 free variable 会出现在 homogeneous 的 solution。All right, so let's start. So I received a very few good questions from your email. You email me some of them. So let's look at them together. So first question people ask to check whether a transformation is 1-to-1. Is it sufficient to check whether the equation Tx equals 0 has only the trivial solution? So where does T came from? This T actually come from the transformation here. So, well, what does it mean by 1-to-1 transformation? Every element in the codomain, there's only at most one pre-image. Okay, so so you need to check that. But here this says what? You only need to check 0.
Okay, I need to check the point 0. Okay, such that this 0 has only one pre-image. Okay. Is it true or false? True? True, because in class I taught before, right? The theorem. But there's one small thing you need to note here. This we only talk about linear transformation here. Only linear. Okay? If it is linear, then you can use this. Only check 1.0. Okay? Only when it is linear. If it's not linear, then you need to go through the original definition. Okay? So this is true only for linear. Okay? This is true for linear transformation. Do you still remember what a linear transformation is? Map that respect factor, addition, and scalar multiplication. What do I mean by that? So for every xy in Rn, t x plus y equals to tx plus ty, okay, and then tcx equals to c times tx, two property. Okay, vector addition and scalar multiplication. Okay, yeah. Only this kind of linear transformation you can just check on the point 0. Okay, if 0 only have a trivial solution, then it is 1 to 1. Okay, I produce a proof for you in class. Okay, so some of you are very concerned. Do we need to prove theorem in quiz? What do you think? Typically, we don't prove theorem in class. I mean, in quizzes. Okay, quizzes were mainly testing whether you know how to do calculation or not. Okay, but in our class, right, you'll see me emphasizing maybe more than what other lecturers do about concept. Why do I do this? Because this is something to do with my own personal philosophy about maths. I don't want you to be scammed. Okay, you understand what is scam? Understand? Scam. You know what is scam? Huh? Scam. What is scam? Huh? You know what is scam? What is a scam? What is scam? In Chinese, what is scam? 被骗. I don't want you to just calculate without knowing what you are calculating. Because why? You will easily calculate wrong stuff. Okay, you will easily don't know what the question asking. Okay, so that's why I will focus on telling you some concept. Okay, but maybe this will make certain people here uneasy because I somehow force you to think. Okay, so you have to like make sense of what I say. I mean, if you don't make sense of what I say, you should come back and check with me. Okay. Typically, when some student ask this type of question, right, you know what they are thinking or not? You know what they are thinking? I mean, about 3 years I teach in SMUM. You know, when they ask this kind of a question, what they are thinking? 其实他们在想什么，在问这题的时候。Actually, they don't really listen to the class. They want to study by themselves. They try to work up their own way. Do you notice? You notice either you or your friend doing these things or not in class. Don't want to listen to lecturer one, study on their own. They think they can pass. Do you understand? Okay. So in my class, make sure you understand everything I say. On the spot, don't understand, it's okay. I provide a recording, right? Okay, you can go back and listen again. If you still don't get it, you should ask me, find me. Okay, I have an office hour, 4 hours for you each week. Okay, this week there's no one coming, but last week there's one. Okay, yeah. So you can come and find me if you don't understand. Okay, you don't need to study on your own one. I'll tell you, okay, what you need to take care. Okay or not? So if you try to study yourself, there's too much thing to study, you know. There's a lot of things to study. So in this class, I will point out the main point for you. Okay, this is the thing I want to test you. Okay, so how to figure out what things I want to test you. It's about what I say in class. So make sure you understand what I say in class. Okay, and once you understand, then I'll start testing you these things. Does it make sense or not? Okay, so make sure you understand what I say. If you don't understand, go and come and ask me. Then we will confirm. Okay, I'll confirm that you know or I know. Maybe sometimes it's my problem. So I maybe say something wrong. Okay, so you need to point out also. Does it make sense? Okay. So so if I didn't ask you to prove, right, you should just specify there's a theorem proof in class and then you use the result. Okay, use it in the right place. And there's a lot of theorem that's without name one. Then how do I know which theorem you refer to? What do you think? I think the theorem no name. How do I expect you to memorize the statement? Huh? I think I mentioned once in class last time. You need to be clear that what condition trigger the result. Okay, tell me that, or I meet the assumption inside my theorem. So by theorem, something is true. Okay, you need to make clear to me what is the assumption that you met. Okay, so for example, since we have this linear transformation, to show that it is one-to-one, we just need to show that Tx equals 0 has the only trivial solution. Okay, so this assumption is very important, linear transformation. Okay, so you need to tell me the assumption, not the statement itself. Okay, this will demonstrate that you really understand the theorem and then you know how to use it. That's all. Okay, you don't need to memorize the whole statement for me. Okay, so the point is you have to understand. Okay, if you memorize, you have no chance, because within 5 weeks, there's a lot of things you need to memorize. Okay, you got no chance actually. So make sure every lecture you understand. Then day by day, bit by bit, you build it up. Okay, okay. For sure, for some of you, this process could be painful. Could be painful actually. Okay, because you never went through this kind of process before. Okay, this is a genuine learning process actually. Okay, it's not just by doing exercise. I change a bit bigger and then you know how to do it. This is a scam. Why is it a scam? Because after you graduate, you forget one. You for sure forget one. You don't even know how to use it in real life. You understand or not? Okay. This is quite common in a maths course. So I mean, student like this ask question. Okay. Yeah. Okay. Third one. Any true or false question in exam? I think we won't do this. Okay, we won't have a true or false question here. Because to test true or false question, actually testing your concept. Okay, so we will test your concept through calculation. Okay, yeah. So we won't go to that high level of testing because in 5 weeks it's also hard. Third is very technical question here already. So this is a very specific example. So one of you asked me, do you need to do this step? Okay, this step. Do you know what this step is? This is the RIEF, right? Okay, so you have these 3 pivot column for your augmented matrix to show that it is consistent. Okay, my claim is no. Okay, depend on what question you want to ask. Okay, let's say the question said I want to find a solution. So you need to do this step so that you can see x1 equals to 1, x2 equals to 2, x3 equals to 3. But to show that it is consistent means what? There is a solution. Okay, so how to show there is a solution? As long as you have pivot in every column in your coefficient matrix, you should know that you can solve it. Okay. Yeah. Okay, so one way is you produce the solution. The other way is to see that if you have pivot in every column, actually you can really solve this system here. Okay. The main problem with inconsistent is when, do you still remember? When you have a row of 0 here in the coefficient matrix. Because if you have a row of 0 here, you need to make sure that the B vector here also have a 0 there. This is the place where you don't, where you have an inconsistent. system. Okay. Okay, once you have all the pivot, actually, you can imagine that you can do your row reduction until the step in the RE. Okay. Any questions so far? Okay, is it clear? Is it clear? Yes. And yes, I mean, no. Be careful. What's your question? So, do you have to have 3 pivot to show that it's consistent? No. The answer is no. A pre-pivot tells you what? There's only one solution actually. Okay. Let's say there's only 2 pivot. Okay. Last row here is 0, 0, 0. But in this case here it's inconsistent because it's 0 equal to 3. But let's say this 3 is 0. Then it is still consistent. Moreover, there's a free variable. Okay, 0, 0, there's a free variable, meaning what? You have a lot of solution actually. Yeah, no. Okay. Yeah. Right. Yeah, good. Okay, any other question that you want to ask? Okay, if no question, I will continue with the elementary matrix that we left last time. Okay, so now I want to continue to give you this idea here. So the idea was you can replace elementary row operation with elementary matrices. And I want to do this through an examples, actually. Okay, I want to do this through an example. So let's say we want to solve this linear system here. Let's say I want to solve linear system here, x1 plus 2, x2, x3 equals to 8, 3x3 equals to 6, x2 plus 3x3 equals to 2. Okay, let's say I want to solve this. Okay, so what do you do? Typically, you will get out your augmented matrix here. So let's do that. Okay, and then you start doing row reduction, right? Okay, so what are the row reduction you could do here? Maybe you can swap row 2 and row 3 first. Okay, and then you want to find your pivot column such that you get 0, 1, 3, 2, 0, 0, 1, 2. And you need to make everything above your pivot position 0, right? Okay, so there are 3 spots to take care here. So what can you do here? First of all, you can take R1 minus R3 or R2 minus 3R3 such that you get this one should be 6, 0, minus 4. And then the other step you take, let's say, R1 minus 2R2. Okay, did everyone get the same answer? You get the same answer as me? 6 minus 8, 14. Is this the answer? You solve it? Things are a bit weird. I think this is 2, isn't it? Okay, we can, we can do the checking, right? Okay, let's do the checking. And let's do checking. See if we have the right answer. Oh, here is 14. is 2 is 2 is minus 4. Okay, do we have the answer or not? So 14 minus 8, you get what? 6 plus 2, 8. Okay, I think it's the right answer. 3 times 2, 6. And then minus 4 plus 6 is 2. Okay, so this is the answer. So, but last week we said that actually what we can think of it is we can think of this elementary row operation as a elementary matrix multiplied to the augmented matrix. Okay, so what's the interchange row corresponds to? What's the matrix it corresponds to? So let's say we start with this. Okay, so how do I figure out the elementary matrix? Okay, that correspond to this action here. Okay, so what should I do? Okay, so the question is, what should I do? Okay, what should you do? You should really do this elementary row operation on the identity matrix. So if you do this row operation on this elementary matrix here, what do you get? You get 1, 0, 0, and 0, 0, 1, and 0, 1, 0. Okay, and then you try and multiply. Okay, try and multiply this matrix into this augmented matrix. Do you get this or not? Okay, first row times first column, first row times second column, first row times the third column. You can see that 1, 2, 1 get fixed. Okay, if you take the second row, multiply all the columns, what happens? You see 0, 0, 1. So the one only here, you can only survive the third row. Okay, so but once you survive the third row, but wait, what did you get? Actually, you get the second row. So meaning what? You push the third row up. Okay, is this what you get? You push the third row up. Okay, and then here, the third row multiply all the columns here, make the second row move to the third row. Right, this is what you get. Does it make sense? Okay, okay. So how to get this matrix? You need to do this row operation on the identity matrix. Okay, you need to do it on the identity matrix. So what size do you get? Actually, you need to get the size on the left-hand side here. Meaning here, what's the number of rows? The number of rows is 3. Okay, so you need to get the size 3 identity matrix. Because on the other side, you should get size 4, right? Okay, so make sure you use the right size. The size of the identity matrix is depending on the number of rows because you are multiplying from the left-hand side. Does it make sense? Okay. Okay, how about this one? How to get this? I think this one is relatively easier. Right? So what's the corresponding matrix, okay, that corresponds to this scaling here? You are scaling the row 3 by 1/3. Okay, so next step, you should multiply by a identity matrix but scale on the third row like this. Does it make sense? Okay, so can you imagine that the first 2 rows here will fix the matrix, the first row of the matrix, and then the last row of the matrix, what do you get? You get 0, 0, 0, 0, 0, and then 1/3 of 3 and 1/3 of 6. Okay, 1. Okay, so this is the second type. How about this? How about this type here? How about this type here? Okay, if you do this on this elementary matrix here, I mean identity matrix here. So let's make this a different color. What's the next operation you get here? How about we move forward? Smaller bit. this way. Okay, so we can arrange it like this. Right. So if I applied it on identity matrix, what do I get here? My row 1 is taken to be row 1 minus row 3. Okay, so in this case here, what happened to this identity matrix here? Row 1 minus row 3. Okay, 1, 1, 1, 0, 0 minus 0, 0, 1. So I should get 1, 0, and minus 1. And then the others will keep the same. Okay, and then this is how you figure out all the rest. All the rest. So this one should get 1, 0, 0, 0, 0, 1. And row 2 minus 3, row 1, row 2 minus 3, row 3, I should get 1 minus 3, like that. Okay, and then the last one. What's the last one? Okay, let me not tell you how to get it. Can you tell me what you get? What's the last matrix that correspond? See if you do the right thing or not. Okay, what's the last one? Can you tell me the entry? What do you start with? 1 minus 2, 0, and then 0, 1, 0, 0, 0, 1. Okay, so this is okay. So you should go back and try. You should go back and try. If you multiply this, do we get the one that we computed using elementary law to confirm? Okay, to confirm. Does it make sense? Any? So far, so good. Okay. Another idea is you do this operation on identity matrix, right? So meaning you can reverse to identity matrix also. These steps are invertible. Okay, these steps are invertible. For example, this one. How do you go back to identity matrix? You swap again. Okay, you swap again. Okay, you swap again. And then how about this one? You scale the third row by a different scalar. So this identity matrix is scaled by 1/3 on third row. So what do you need to do to make this 1/3 into 3? You multiply by 3. Okay. And then how about this one? How about this one? R1 plus R3. Okay, so we do experiment. So actually max is about experiment. So let's do this. So let's say 1, 0, minus 1, 0, 1, 0, 0, 0, 1. Okay. So let's say we say that by doing row 3, so our goal is to make this into identity. Okay, make this multiplication to identity. So we know that this matrix is correspond to R1 minus R3. So to make it into identity, we need to make this minus 1 disappear. Okay, so your suggestion was take row 1 plus row 3. Okay, so let's write down the elementary matrix that correspond to row 1. We should get 1, 0, 1, 0, 1, 0, and 0, 0, 1. So do you multiply to this matrix or not? Can you test? Can you test? So first row, first column, only 1 multiplied together, and then the other 2 is 0. First row, second column, okay, you get 1 times 0, 0 times 1, 1 times 0, so 0. 0, 1, 0, 1 times negative 1, 0, 1, what do you get? Negative 1, 0, and 1. So they add up to 0. Okay, so similarly, you should check this term. You also get the leftover for your identity matrix. Okay, no? Yeah. Okay. So when every time you do this computation, can you see what does this? Why this identity matrix acts like an identity? Why? Because when you take this first row, multiply all the columns, what happens? Only the first row of those columns save. Okay. And then second row, you save the second row of all columns. The third row, you save all the third row from the third column. So that's why this is the identity matrix. Okay, that's why this diagonal is pretty important. Okay, first row is saving the first row in all the columns. Second row is saving the second row in all the columns. Like that. Does it make sense? Okay. Any question so far? If I go too far, please slow me down. You can ask me a question. Okay. All right. So next theorem here that we haven't gone into last time. So it said that n by n matrix or square matrix is invertible. Invertible means what? There is a inverse. Okay, there is a. So this implies that there exists an inverse matrix such that A inverse A and A inverse is the identity matrix. Okay. If and only if it is row equivalent to In. So what does this mean here? Row equivalent to In, meaning what? You can do a bunch of elementary row operation, okay, such that you get the identity. Okay. Row equivalence. So you can do the elementary row operation such that you get to identity. Okay. So this statement here is if and only if. Okay, if and only if. Which direction you think is easy to see? Now, which direction is easy to see? Left to right or right to left? Want to try? Guess first. Left to right or right to left? Want to try? I see some of you like this, I don't know which way. Right to left or left to right? Right to left. Correct, right? Why is it right to left? So if you have a bunch of things that multiply to identity, right? Who is the I inverse? You just take this product of EI to be your I inverse, A inverse. Okay, so, right. So if, so we have this direction here. If we have EN up to, E1 up to EN that multiply A to identity, who should we take for our A inverse? We just pick A inverse to be the product of En. It's a matrix, right? Okay, so this is a matrix. Let's solve this equation. Okay, so the harder part to see is if it is invertible, then you can reduce it to the identity matrix. Okay. I think we won't pursue this. So the other direction is true, but we won't prove it us. Okay. So what I want you get, what do I want you to get out of here is to check that whether a matrix is invertible or not. What do? You just do row reduction. Okay, see if the RREF is identity or not. Okay, so the upshot, let me put the upshot here. To check n by n matrix is invertible. You can do, not need, you can do REF. You can do row reduction. Maybe you just say row reduce. So you can row reduce A to see if the RREF of A equals to identity matrix. Okay, if it is not, then it is not invertible. Okay, Why I don't say you need to do this? Because later we'll see different way to see whether a matrix is invertible or not. This is one way. Okay, this is one way. You can do row reduction to see whether the REF is the identity. Okay, because why? Last time we got the theorem, right? Every matrix only has one and only one REF. Okay, you cannot change from non-identity to identity. No. So it's very specific. Does it make sense? Okay. Are you convinced or not? Because if your REF have a zero rows, you can never create non-zero rows from that zero rows. You understand? Okay. You cannot. Okay. So now there's an algorithm for finding this inverse, okay, from this idea of this theorem here. So what do you do? Again, we want to set out augmented matrix here. What do we set out here? If you want to find the inverse of A, so you just put A on one side, put identity matrix on the other side. Okay, and then you row reduce it. Row reduce it such that this A side here become an identity matrix. So what's left over here is A inverse. Okay, so this is the idea. So why this works? So let me tell you why this works. So let's say we have this. So basically we have this. Okay. So we try to row reduce. We try to row reduce this side to identity, and then the other side is multiplied by I. Okay, multiplied by I. So basically, is this whole bunch of things multiplied to I again. Multiplied to I on one side. Okay, so this is a bunch of things, and then this is what we call the inverse. Correct or not? Just now we say that we just take the product of this. This is the inverse of A because it satisfies something times A equals to identity. Okay, does it make sense? Okay, so meaning what? Meaning what? Meaning this one is just like how to say a recording what you are doing. Okay, and then you put this record together, you will get a inverse you want. Does it make sense? Because identity matrix really doesn't do anything to all of them, right? It doesn't do anything because it's not identity matrix. Okay, so once you set out this augmented matrix, you are really row reducing A to identity only. And then the other part, it is recording what you are doing. And then this is the inverse that you need. Does it make sense? Okay, so let's try. So let's try this question here. Can we do it together? Let's do it together. Okay, try and row. The goal is to row reduce this augmented matrix by setting A on one side and then ID matrix on the other side. Okay, try and row reduce this. Any question? Understand you know what you do? You know what you have to do? If not, I can repeat again. Okay, so try and row reduce this such that this on the left hand side you get identity. And then the right hand side will record what is the A inverse you get. Okay, I give you 2 minutes to try. Okay, so let's see. So what do I do for the first step? So because the first column, first row is not a pivot position yet, so I move the second row up. It's okay if your step is not exactly same as me, but see if we have the same answer or not. So then what do I do? After that, we make everything below the first pivot position 0. Okay, so I take R3 minus 4R1. And then we have automatically we have this second pivot already on the second column. So we make that to 0 also. So I take row 3 plus 3 row 2. Okay, and then we have a nice 3 pivot position here. So I make the last pivot position to be leading entry 1. Okay, and then I remove all the 0. Okay, so in the end I get this matrix here. Does anyone get the same one? You get the same one? Same? Okay. How to check? How to check whether you get the right answer or not? Like you must check. How to check? Huh? What can you check? What do you do? What do you do once you get this? How do you check this is the right inverse for that A matrix here? You do A times the answer you get. See if you get the identity or not. Okay, if not, there might be some calculation error. Okay, is it clear? Yeah. Okay. So the other one I will left for exercise. Okay, so you can do this also. But I can give you a hint here. So I think this augmented matrix is not consistent. Okay. Yeah, so you will get a not row equivalent to identity. So the inverse don't exist. Let's see if your calculation give you that or not. All right. Okay, so let's go to the next part first. So this one I go left as homework. So the hint is this matrix is not row equivalent to identity. The matrix. Let's see if you get the same coverage. Okay, let's go to the next part first before we're having a break. Okay, now we're gonna introduce the subspaces of Rn. In the chapter 4, we will see vector space and subspace again. Okay, so this is the first space you see subspace. Okay, so subspace actually built up by two words here. It's a subset and a vector space. Okay, it's a subset of the set, and then this set is a vector space. So a subset of Rn is a subspace that satisfies this three property here. Okay, so there are three property here. Again, did you see some principle coming out again? Do you see? What did you see? Vector addition and scalar multiplication. Okay, so this is very important operation in vector space that you have to always remember. Okay, in a vector space, you need to know how to do vector addition. You need to know how to do scalar multiplication here. So to satisfy this subspace condition here, there are three conditions. First, the zero vector must live inside this H. Okay, the zero vector must live inside this H here. And for any two vector inside your subspace, you add them together, it still live inside your subspace. So this is what we call a closed under addition. Okay, it is closed under addition. So your number is also closed, right? For example, 2 plus 3, 5. Okay, still live in the same number space. Okay, closed under addition. And also closed under scalar multiplication. So if you have a vector and then you take a scalar, multiply your vector, it still live inside your subset. Yeah. Okay. Actually, right. Actually, one of this condition is redundant. One of this condition is redundant. Meaning you can get one from the other. Which one do you think? Both of them are redundant, or which one is redundant? meaning can be obtained through the other. The third one can be obtained from the second. How do you do it? Yeah, continue. CU equals what? So you are implying C is a integer or natural number. But how about C to be 0.2, let's say? Real. Yeah. So just now you are considering like 2U, 3U, 4U, 5U, right? How about 0.2U? Okay. So actually, 3 implies what? Okay. How do you get zero vector from this kind of function? Yes, good. You just pick C to be 0. Then this line will tell you 0 times anything is in, but 0 times anything is 0 vector. So in the exam, if you just check these 2 is also enough. Okay, but if you want to check 3 also. Okay. I mean, in this case here, this condition here become easy when you want to check something is not a subspace. You just check that whether zero vector is in there. It's not. If it's not in there, then it is not a subspace. Does it make sense? Okay. Maybe to show something is a subspace is not very useful here because you're gonna do it in 3 anyway. But to show something is not a subspace, then this is very useful. Go and test the zero vector first. If zero vector is not in there, then good. It's not a subspace. Okay. Don't worry. I'll give you an example. I'll give you an example. So maybe I motivate you with some geometry first. Okay, I motivate you with a geometry, and then we can take a break and then come back for examples. Okay. So in the geometry sense, what we are doing actually here. Okay. So for example, we are just looking at R2 first. Okay. For example, R2. So R2 we can draw, so it's good. So what is subspace of R2 here actually? So you must include the zero vector. Okay, you must include this origin here. Okay, so let's use different color. You must include this origin here, right? Okay, and then all the scalar multiple need to live inside. Okay, so if you have any vector, all the scalar multiple must live inside. Okay, and then I claim that this form a subspace. Okay, this lines form a subspace. Why? If you take all the multiple, if you add them together, it's still a multiple of a vector. Okay, so this is one of the subspace in R2. Okay, what is not a subspace? Okay, so let's say this is a subspace. Why is not a subspace? If I rotate and translate this line a bit, this is not a subspace already. Why? Why is it not a subspace? Because there's no zero vector inside this line here. Okay. Okay. So, so what does it mean here? So what does it mean here? Why this line is subspace, this line is not subspace? How do you think about these lines here actually? Actually, the correct way to think about this line, right, is through the vector. Okay, through the point here. Okay, it's through this point here. Can you see it? Okay, it's through this point here. Okay, so if you can notice, if you look at this line here, if you look at this subspace line here, the vector, all the vector on this point lie on the same line. Does it make sense? Okay. So you can see that if you look at this horizontal line here, the vector that corresponds to all these points looks like this. So I mean, let's say I want to make this line into a subspace. What do I need to do? I need to take this vector and then add them together. Have you learned addition vector in the picture form? The resultant force, something like that. Okay, so if you add this, let's say if I add this two vector together, as I add these two together, I should get this parallelogram thing, right? Okay, so meaning what? I need to fill out all the parallelogram. Fill it out. Okay. Yeah. Including this point in adding in. And then we fill out. Does it make sense? Okay. So you need to check for this three condition. And then how about scalar? Scalar means what? You need to include all these points in also. I don't know. All the line you need to add in. So can you imagine that if I'm gonna make this line to a subspace, what do you get? You actually get everything. You should get everything. Okay, if you scale every line here, basically you get everything. Yeah. Right. Yeah. Okay. Yeah. So this is not subspace. Later we'll see some more example about subspace. So let's break until 402. This one, because the first condition you need to have a zero vector inside.
Yeah, but in geometry, like why it's not subspace?
Because zero vector is here. So this line has no zero.
Okay, so any line that intersects the point 0, 0, it's a subspace.
Yes, but you need to show it. Yes, it is true. But you need to show it. Yeah.
How to show it?
How to show it? Okay.
So the other.
Check. Yeah, check the other two conditions. Yeah.
是这个
Yes.
这个问题
Yes. Yes.
就是在哪个地方？
应该是在 lay 里面吧。但是我建议，我有个建议。我建议不建议。
哦，
有吗？有看到？对，这个是我的建议，但是我有告诉你说，可能我没有写，这是我没有写。哦，这里，就是说这个是应该是 Chapter 5的书来的，所以我写的这些是 Chapter 6，这是 Chapter 6。但是如果你跟着那个 Chapter 5的题目去做 Chapter 6的，也是差不多。
哦，
其实。
然后还有这个。这个的话，它有答案吗？
这是什么啊？这从哪来？
也是在这个里。
哦，我解释了，给我看一下。
但是
这个吗？
哦，
这个还是这个？这个
应该不是 notes
哦，OK，
应该是
哪一个？这个招啊，是那个招的，所以那个招的应该是这个周分啊，不是周分。那个再看一下它题。哦，是书来的这个。
对对。
这个我没找过哎。
哦，
可能我没有吧。
哦，
我有给2本对吗？
哦，
对，这本，这本，这个我没有找过答案的，其实。
哦，
呀，这里也是有很多习题的。你要不要试下找找看？
行，
你知道去哪里找？
用ChatGPT 找。
有一个叫 litgen.io 啊 ，LIT，可以直接找的。你就打他那本书，然后 solution manual 看一下里面。
谢谢。
对。好，是不是有问题啊？换了，他会换他的那个网址，
谢谢。
不然我如果找到，我就告诉你。
The duration 多长？
大概15分钟。
多少题
？4题短。
那应用题 application 会做？
什么叫应用题？
它是给你一个 situation，让你有的人蛮多应用。
对，不会。
也不会这样。
要打球啊！
今天没有，今天没有空。
就是说这个的话，如果是23减21得到后就23+4。
哦，它的 inverse 它
对，但是
嗯哼
这个话它是想成一个一样的来得到它的应，
对
到底有什么？
对，有什么哈？就是有什么，就是说我们要我们的目标是这个，因为我们目标是这个，所以意思说，比如说我给了你这一个嘛，你的目标是说怎样把这个2弄不见，然后把这个1变减，所以要怎么
所以就是，所以它并不是说
啊？
这个就能得到，它要看。
对，但是也有一种方法吧，如果你要问的话，就是说，因为这个新的这条是，因为你想啊，你想想看啊，这个东西怎么来？因为你可以记录，用这个记录，其实如果要的话，就是说新的这一条是叫它 R3 啥，然后现在你应该要做的事情是什么？找回旧的那一条，因为这个旧的这一条是这一条，所以要怎么找回旧的这一条，就会告诉你你要做什么。其实你如果搬过来的话，好像也是这个，
对，
对吧？你变成 R3就等于，因为这个是新的 R3了嘛，所以叫它这个，因为这一条叫做 R33嘛。Yes，
就是我知道这个矩阵之后，我
对
问他这个
找回旧的那个 R3，对，所以你看一下它的步骤其实也是一样的。
但是有的时候就
对
不太一样，它的符号会有变。
对，所以所以最容易记的就是你的目标是这一个就对了。
所以其实还是不能，
记这个方法也可以吧，我觉得，
因为我
因为如果你用在
这个的话就是+4而已。
对，没有错，因为如果你用这个原理，用这个方法，能不能找到这个减 R4？我觉得能啊，因为你看新的这一条是 R3 star，所以你要找回旧的那一条的话，就是等于 R3 star 减4R1，对呢，减跑出来啊，也可以，我觉得这个方法也可以，但是它的原理就是说，我要做一个步骤，such that 我拿回
原来的
identity matrix，也不是原来那个
对
identity
这
matrix，
个
原来是这个。
我想问，如果想找到 base，这个是一定要画成简化的这个吗？还是只要画成这样子就可以？
哦，其实到这一个就看得出来，
哦，所以
对，
如果要问的话，就只要
没有错
我不一定说一定要画成最后这个。
不用，
哦，
对，其实不用。
谢谢。
所以我想问你
，Yeah，
，Rn 去 Rn 到是什么意思？我就想
就是
三型 matrix 去另外一个什么？
不是，这个是 vector 来的，这个 Rn 去 Rm 是这个是一个 map 嘛，这个是一个 function 嘛，对不对？所以 function 干嘛呢？就是给一个 input，给一个 output，所以它 input 是 Rn 里面的 vector，output 是 Rm 的 vector，就这样。然后这个 function 可以写成 matrix。
然后讲 determine n 跟 m，
题目要给的，题目要给
啊
的，对，题目要给的，它会定下来，R2去 R3呢，还是 R3去 R4？
这样它这个 n 跟 m 代表什么？
可以变，它们可以不一样。
讲可不可以不一样？
就是说，
好像这个3去2，
对，then 这个 n 就是3，这个 m 就是2，then 这个情况的话，n 是2，m 是2，就是说你可以选择的这个 n 跟这个 n 跟 m 你可以选择。
它就只是一个代表了，没有意思，还是有意思。
那意思就是说，有意思的，有意思的，就是说，有意思的，有意思，就是你这个情况的话，它是 R2去 R3嘛，所以你看它 input 的东西只有 R2里面的东西，output 出来它是在3维里面，之前在2维，之后在3。
可是它也是有思路的，
哪里？有，可以啊，
是也是
可以啊，可以啊。这个 n 跟 m 是在1到
1到5线里面选的，好吗？会给。你是什么系啊
？CME。
哦，CME。OK， 好。
这道题。
哦，OK。Image of 这个column of n by n identity 你知道是什么？就是1、2、1、3、1、4到1n 哦。然后它这个说 column 它是所以它是说你这个 linear transformation 的 standard matrix 就是那个给你一个 t 你就有一个 a 嘛。然后那些 a 怎么来的？还记得吗？某一个 theorem 说这个a 是从 t apply 去1、1，t apply 去1、2，apply 去 t3，apply 去4，就是说 image on 这个1、1、1、2、1、3、1、4到1，明白 ？OK， 不然等一下再解释，因为要上课先，然后再给你解释。Okay, so let's see what are the examples here. Okay, so I give you some geometry example. How about this example here? Given any vectors in V1 to Vp in Rn, okay, we want to see that span of V1, V2 up to Vp is a subspace of Rn. So first of all, still can recall what's the definition of span of V1 up to Vn, Vp? What's this definition here? So this is a set, right? So what is in here? This is a set of what? Set of linear combination, okay, of V1 to Vp. So what does it mean by linear combination of V1 out to Vp? C1 times V1 plus C2 times V2 plus up to Cp times Vp, okay, for all C1 up to Cp in R, for any C1 out to Cp. Okay, right. So to show subspace, right, how many conditions you need to show? You need to show for 3 conditions here. Okay. So the first condition is whether this C here, okay, let's give some notation here so that we don't need to write the long span here. So let's call it X. So the first question is 0 in X or not? Is 0 in X? Is 0 vector here or not? Yes, so why? Why? So, okay, to show that something is in this set, meaning what? You need to show that it satisfies this condition here. You need to be able to write it as a linear combination of this vector. Okay, so how to write? So the question turns into how to write the 0 vector in terms of linear combination. So the choice here is what? Okay, so where's the choice here? V1, V2 out to Vp is fixed already. Okay, so what's the choice here? The choice here is the scalar multiple. Any scalar multiple you can pick. Okay, so can you pick? You just pick all the C to be 0. Okay, so you just pick all the C to be 0. How about second one? Okay, second one says what? If U and W in X, then U plus W must also be in X. Okay, so we need to show this. Right. So if we don't know anything about U and W, you really cannot see it. But what do we know here? If they live in X means what? They are the linear combination of V1 to Vp. Meaning what? So we can write U as a linear combination of linear combination of V1 up to Vp. Okay, so for sum, okay, for sum, you still remember the notation here for sum C1 up to Cp. Okay, we don't know what is a scalar, but it doesn't matter really. Okay, it doesn't matter. And then W, potentially, you will have another set of coefficient, correct or not? Okay, you could have another set of coefficient. Okay, potentially you got another set of coefficient here. And then you add them together. Okay, so you add them together. Okay, so you got a big sum here. A big sum here. Okay, so what can you do to this big sum? What do you reckon? So the question is whether you can write it as a linear combination with V1, V2 out to Vp again. Okay, so can you do that? How? You want to try? Try? What's your name? I forget your name. Edward. Oh yeah, right, Edward. So Edward, what do you reckon you can do next? Okay. Okay, so take out means what? I should put the like term together, right? So I put all the VI's together. I mean, put all the V1s and V1 together, and then V2 and V2 together. Why can I do that? Because our vector addition is commutative. Okay, I can swap in particular. Okay, so we can swap. And then we can do factorization, right? Okay, or in other words, what do we call it? We call it distributive. Okay, distributivity. Okay, we can distribute it. Or in high school, you call it factorization. Okay, we can do distributivity. Then we are good. Why are we good? Because we write U plus W as a linear combination of V1 up to Vp. And then what's the scalar part? The scalar part is just adding out the scalar term from both V I. Okay, right. We add two scalar, it is still a scalar. Okay, yeah. So you could imagine that we do the same for Cu, for example. Okay, if we multiply C to a whole vector here, take any C in R, you can see that we also can write Cu as a linear combination of V1 to Vp. What are the coefficient here? You also do distributivity such that you get CCR. Okay, CCR. C times C2. C times CP. Okay, so your new coefficient is C times the old coefficient. Is it clear? Question 4. Okay. The point is, the point of showing subspace is you need to understand the set here. Okay, you need to understand how to satisfy the set condition. I think that's the hard part. Okay, you need to think of. Yeah. Do you have a textbook with you or not? Do you have a different set from your textbook? Can you throw me an example? Maybe we can do one more together. Can you throw me one example from your textbook showing something is a subspace from this section? 2.8. Anyone find one example? We can do it together. Yes. Textbook with you? Can you give me a set? You show me also can. Let's do the other one together before we get into new stuff. Anyone found one? Yeah, textbook review. Any textbook with you? Or maybe show me the textbook. Then I find. No textbook. No one have textbook. Like this. Only picture, mostly picture. We leave it for next part. Because we will see this concept again actually in chapter 4. We do it now. Okay, so textbook only teach you geometry. It's called it. Okay, maybe then we will leave it to next time then. I will see it again in chapter 4 actually. Okay, so for now, we will do what's a column space. Okay, so we'll define a column space for m times n matrix here. So imagine you need to imagine this matrix. Once I tell you what m times n means what, the number of row is m, number of column is n. Okay, you need to expand the matrix out inside your mind. And then what does it mean by a column space? Okay, so you need to imagine column of a matrix, right? So you need to split your A into vertical line, right? Okay, like that, column. Okay, so what does it mean by column space here? Is the set of all linear combination of the columns. So meaning what? You take your A, you split into columns, and then you look at the linear combination of this column. And then we call it a column space. Okay, meaning what? Column space is a span of what? So let's say my A split into A1, A2, up to A. How many A? I test you. What's the size here? M or AN? M or N? N, okay. So number of column here. So set of this. So column of A here actually is defined by what? The span of A1 up to A and A1. Okay, set of. Okay, and then show that co A is a subspace of Rn. I claim that I have shown this. Okay, I claim that I have shown this. Why? Because in the previous example, what did we show? Given any set of vector, we show that the span of the vector is a subspace. Here, this is a span of a specific vector coming from your matrix. Okay, so the proof is exactly the same. Okay, as what we did just now. Okay, no? Okay, so that's why you can see when we do maths, we introduce stuff in a chronological order or logical order. Okay, the one that we want to introduce first is what we want to use later. Okay or not? Okay. Yeah. So there's no reason we simply introduce stuff. It must be that we want to use it, so that we will introduce it, and then we move on. Okay. So this is a special part about maths. Okay. So next question is, I give you a matrix A, I give you a vector B. Determine whether B is in the column space of A. Okay, so let's write it down mathematically. So whether B is in the co-A or not. But what does this mean by definition? Whether B is in the span of the column of A or not. But what does this span mean? You want to ask whether there exists C1, C2, C3 such that B is the linear combination of A1 up to A3. But what is this? Isn't it this is a vector equation? This is a vector equation, right? If you cannot see, let's write it down. 3 minus 4 equals to C1 times 1 minus 4 minus 3 plus C2 times minus 3, 6, 7 plus C3 times minus 4 minus 2, 6. Right. What is this? This is also equivalent to what? a matrix vector equation. 1 minus 4, 3, minus 3, 6, 7. Sorry, there's one more line. Minus 4, minus 2, 6 times C1, C2, and C3. But to solve for this, this is exactly solving for the augmented matrix, right? 1 minus 3 minus 4 minus 4, 6 minus 2, 3, 7, 6 on 3, 3 minus 4. Okay, so meaning what? You want to ask whether this linear system is consistent or not. Okay, yeah, you see, we create another language again, called space. Okay, the point is, if we introduce so many terminology here, is because we want to make things more generalized. Okay, later on we will talk about Coulomb space. Okay, let's not compute this. Okay, you can try and check at home. I will provide solution. I think the answer to this is a consistent system. Okay, it's a consistent system. Okay. Okay, I left this exercise to you to compute at home. Okay, next part. Row space. Okay, so column space. I tell you how to chop the matrix into vertical lines, right? So row space, you should imagine that you can chop it into horizontal. Okay, so it is chopping into horizontal because it's the set of linear combination of the rows of A. Okay, rows of A. So how do you imagine rows of A as a vector? How do you imagine? What do you reckon? How do you imagine? Okay, how about I ask you another question first? So if I chop these m times n matrix into columns, okay, so there are n columns, right? But where does this vector live in? What do you think? How many number inside this vector here? Rm or Rn? Huh? M, right? Okay, because the length is m, number of row. But if you chop into horizontal vectors, so you how many rows you have? A1 to A, M. But where do they live in? Actually, they live in Rn. Okay. So you also can like write it vertically actually. Okay, you can write it vertically. Okay, so it's really a vector. And then show that it is a subspace of Rn. I also claim that we have done this already. Why? Because row space of A is just okay. Let's say B. Let's not use A, otherwise maybe we're confused. So let's call these B, I. Yeah. So these are the span of BI. But we already shown it for a general what? General vector. Okay, so these are just some specific. Yeah. Yeah. Okay. So the main takeaway here is you need to understand that when I give you a set of vector, you look at the span, they form a subspace. Okay, lastly, okay, this is also very important, null space. So null here means 0. Okay, so what is 0 about this space here? So this is the set, all the vector that when you do a matrix multiplication with A, you get 0. Okay, this is called a null space. And anything multiplied to A, you get 0 is living inside this null space. So these are the vector that makes your matrix, that get 0 vector after multiplying with your matrix. Okay, I cannot say make your matrix into 0 because what you get out is not a matrix. I mean, it's not the same size as A. It's a vector. Okay. Okay. Maybe it is fun to show that this is a subspace because this is not span anymore, right? It's not defined as a span. Maybe I write down this form for you. Easy to see. So now A is equals to everything that multiply A to 0. Okay. Okay, how about I ask you a question? Which are N or Rm this now A have to live? M or Rn? Huh? N or M? Huh? So here the size of A is M times N, right? So what does it make sense to put Rm or Rn here to multiply? N, right? Okay. M times N, N times 1. So you get a M times 1. Okay, so this one is a N times 1 size such that you get this 0 vector as a M times 1 size. Still remember? Okay, matrix multiplication. So matrix vector. Okay, matrix multiplication is a generalization of matrix vector multiplication. So this X should live in Rn. Okay, let's show that this is a subspace here. Okay, how to show that this is a subspace? So first, you need to ask yourself whether 0 vector is in null A or not. Okay, but to satisfy this condition, right, what do you need to show? You need to ask yourself whether A times 0 get 0 or not. A times 0 gets 0. Yeah, right. Because A times 0 means what? All the coefficient of your column of A is 0. Okay, so it is inside A because A times 0, you get what? 0 times all the column. And then taking the sum. But this is just 0. Okay. Okay. So another way you see that this 0 vector is a M times 1 vector because column of A is living in Rm. Okay, there are M number of rows. So these are all in Rm also. Okay. Right. What are the next thing you need to see? Second, you need to show that if xy in null A, you need to show that x plus y is in null A. Okay, in other words, what do you need to show? You need to show that A apply to x plus y, you should get 0. Okay, you need to satisfy this set condition here. Okay. But is it equal to 0 or not? Okay, I think last time we discussed that it is linear. Okay, it's distribute over these multiplication. Okay, but we know that x and y are both in null A, meaning what? The both sides should get 0. So you get 0 plus 0, which is 0. Okay. So far, so good. Any question? Can follow? Okay, how about last one? Okay, if x is in null A, what do we need to do? Then Cx is also in null A. Okay, so meaning we want to show that A Cx is 0. Okay, but from the matrix multiplication property, right, what can we do? We can straight away pull the scalar out. Okay, we can pull the scalar all the way out. Then we will left with Ax again. But x is in null A, so you get C times 0. Okay, so you get the 0 factor. Okay, so far, so good. Any question? Question? Okay. Okay. All right. Right. So now we will just discuss about column space, row space, and null space. Later in chapter 4, we will see more exotic, not exotic, but different subspace. Okay. All right. So any question before we move to the next part after subspace? Any question? Okay, if no question, we go to this very important concept here, which is called the basis. Okay, let's highlight it. Okay, basis. Okay, basis is a very important concept in a linear algebra. This is one of the concepts that we use to define dimension. Okay, so basis again consists of two things. So basis for subspace. Okay, so we define basis for subspace of Rn is a linearly independent set in H that spans H. So two conditions here. Linearly independent and span. Okay, so what does linearly independent mean? Meaning what? If you set out the homogeneous linear system, right? C1 times V1 plus C2 times V2 and so on equals 0. The only solution is the trivial solution. Okay, so there's no linear dependent equation between them. Spans means what? Every vector, every element in H must be able to write in terms of linear transform, linear combination of vector in this basis here. Okay, so how to imagine this basis? I think I need to write it down. So this basis, right, is a set of vector. Okay, maybe infinite. Is a set of vector in H such that beta is linearly independent and span H. Okay, so two conditions here. Is a set of vector. Okay, this basis is a set of vector such that all the vector inside is linearly independent and then it's span H. Okay, so I'll give you an example. So this example, this is the object we've seen before. Okay, when we want to build the linear transformation, right? Okay, we use TE1, TE2, TE3 up to TN to find the associated standard matrix. Okay, so we will see that this standard basis satisfy this condition, two conditions here, linearly independent and span. Okay, so let's prove this. Okay, let's prove this. So first condition, we want to show that it is linearly independent. Okay, so let's call this set B. So first B is linearly independent. Okay, so what do we need to do? So for C1, E1 plus C2, E2 plus up to Cn, En equals 0, we must have what? We must have C1 up to Cn to be 0. Okay. Again, what is this? This is a vector equation. Okay, so we can set out the augmented matrix. So what does the augmented matrix looks like? 1, 0, 0, 0, 0, a lot of 0, n 0, n minus 1, 0, and then 0, 1, 0, 0, 0, 0, and then all the way up to 0, 0, 0, 0, 0, 1. Okay, and then this is the augmented homogeneous linear system, right? So we got all 0 on one side. But what's this? This matrix is already in a RREF form, right? Can you read out the solution? X1 equals to 0, X2 equals to. Okay, in this case, it's not X, right? It's C. So C1 equals to 0, C2 equals 0, C3 equals 0. So this is already in RREF form. Okay, so it's nice, right? So you can see that this standard basis is what? Is a column from your identity matrix. Column from identity. And then it's in a RREF form. Okay, so you can read out the solution. Okay, so I would say that this is already in RREF. Okay, such that C1 equals to C2 equals to Cn equals to 0. Okay, yeah. Any question so far? Okay, so this is about a linearly independent. Linearly independent. How about span? So what's the differences between span and linearly independent? Span, you need to talk about different B here. For every B, so for any B, so okay. If we're gonna talk about span, B span H means what? For every vector inside H, we need to write it as a linear combination of DC. Does it make sense? So meaning what? I need to replace all the 0 here, becomes some B1, B2, B3, B4, B5 up to B. And can you do that or not? Can we find CI that do it? Can we find CI that do it or not? Can we? Can you see that it's already in REF form already? Meaning what? C1 must be B1, C2 must be B2, C3 must be B3, Cn must be B. Okay. So this standard basis actually build out this nice REF for you. Okay, it makes sense, right? I mean, okay, if you are not familiar with this N knowledge and language here, if you just look at R2, right? Okay, if you just look at R2, so the standard basis is 1, 0, and 0, 1. But if you take any xy in R2, you can literally write it as x times 1, 0 plus y times 0, 1. And this is what you find here. C1 equals to B1, C2 equals to B2. And C1 equals to X, C2 equals to Y. Okay. So in other words, what this standard basis are doing? The first standard basis read out the first spot. Second standard basis read out the second spot. Then similarly for the other I standard basis, you read out the I spot. So EI read out the I spot. That's all. Okay. Okay. Why read out the I spot? Because you look at this REF. If you don't want to look at this REF, you also can look at the actual vector equation here. Also can. Okay, there are a few ways to see. Okay. So far, any question? Question? Okay. Okay, good. So we still got time. So let's do this. So find a basis for the null space of A. Okay, let's find a basis for null space of A. Maybe I think maybe you don't know how to start. So let me start it for you. Okay, so we want to find a null space for A. Meaning what? We want to look at all the vector that multiply with A, you get 0. Okay, so meaning what? You want to find the solution to the homogeneous linear equation. Okay, so what's the augmented matrix looks like? You want to augment a 0 vector. Okay, so can you try row reduce this? Later I will teach you how to read the answer. Try row reduce this. Okay, before that, where should this now A live in? Where are this X live in? There are two choices here. R3 or R5? R5, right? R5. Why? Because you need to multiply the vector from the left. Okay, so 5 match with 5. Yeah. Okay, so try and row reduce this. I'll teach you how to see the solution. Okay, maybe take one page of handle first. It's Du Jiawei here. Du Jiawei, okay. Li Yahan, Li Yanxuan, Gong Jiaming, Jia Senqi,涂天天，涂天天 ，OK。王月豪、严子轩、秦少芬、秦少芬有呢？Dan Daniel, Daniel, where are you? Sorry, later you told me. Okay. Dong Hongwei, Kok Minzhou, Lin Kejun, okay. Yu, Lu Xingyu. Oh, here, okay. Bryson, Hu Chun, Zheng Yao, Yang Fangling, Ruan Qiuzi, Wang Yunxi, Li Zizhen, Xing Yu, Miao Xingyi, Nicole Tong, Xua Yujie, okay. Cao Ziyu, Zheng Yu. All right. So let's compare solution here. Let's not write down the step. I will show you in my lecture note, but let's compare the final solution. I get 1 minus 2, 0 minus 1, 3, 0, 0, 1, 2 minus 2, 0, 0, 0, 0, 0, 1, 0, 0, 0. You get this? Okay, so if you get this, try and get the parametric form. So get the parametric form. In this case here, parametric form is more convenient because we are talking about vectors solution. So do you get x2 times 2, 1, 0, 0, 0 plus x4 times 1, 0, 2, negative 2, 1, 0 plus x5 on minus 3, 0, 2, 0, 1. Everyone got this? Parametric vector form. Okay, one hint, seeing you come to my class, I give you some hint on quiz, must know how to write in this form, parametric vector form. You must learn how to write this form. Okay, everyone got this parametric vector form? Okay, so once you see this, right, what did you see? Just now we say that the null A is a subset of R5, correct? See, got 5 number, right? 1, 2, 3, 4, 5, R5, okay? And then you write it as what? Sum of 3 R5 vector with what? We call it addition with scalar. Okay, meaning what? This solution is a linear combination of these 3 vectors here. Okay, so we can see that. What do we see? Now A is equal to the span of 2, 1, 0, 0, 0 and 1, 0, negative 2, 1, 0 and negative 3, 0, 2, 0. Okay. So we know that it's in the span of this tree. But the question says what? Basis. Okay, basis means what? We know it's a span already, right? Still left with what information you need to check? Are they linearly independent? Okay, so you have to ask whether these 3 vectors are linearly independent or not. Meaning what? Okay, go back to your definition. What do you need to check? For C1 times the first vector plus C2 times the second vector plus C3 times the third vector equal to 0, we must only get the 0 solution. Okay, again, so to solve this problem, what do you need to do? You need to raw reduce the augmented matrix built up by these three vectors. Okay, so you need to do another augmented matrix row reduction on 2, 1, 0, 0, 0, 1, 0, -2, 1, 0, -3, 0, 2, 0. Okay. We quickly do this. Let's see. I have answer with me. Have answer. So let's quickly do this. So let's identify some pivot here. Let's identify a. So I like this row here. I like this row. Do you like this row? You like this row, right? Okay, because it's a 1, 0, 0, nice pivot row. Okay, pivot row. So let's move this up. 1, 0, 0. And actually, there's nice pivot coming out already, right? In particular, these two rows here. Okay, let's move this through these two rows up. Let's move them up. So let's move it to row with row 4 and then row 3 with row 5. Such that we get row 3 with row 5. So get 3. Okay, so can we easily see that we can row reduce the last part to 0, everything. And right. Okay, so if you take this one minus 2 row 1, row 4 minus 2 row 1, and then after that you take row 4 minus row 2, and then you take row 4 minus 3 row 3, and then similarly for the last row you should add to 2 row 2 and then minus 2 row 3, and then you can make everything 0. And then you get C1 equals 0, C2 is 0 equals 0, C3 equals 0. Okay, so they are linearly independent. Okay, so we see that the maybe row reducing. See that C1 equals C2 equals C3. So meaning what? Meaning the set of this set here. Maybe bring it down. The set. Let's see. So this set is linearly independent. Hence, this set form a basis for now. Okay, from this. Span and linearly independent. Okay, whenever we talk about basis, it must span and linearly independent. Okay. So think about it. Why is it span and linearly independent? What time is it? Why is it span and linearly independent? So to form a basis, right, you need to be able to build everything inside of vector space. Okay, so it's span. And then linearly independent, why? Why? Why we want to make sure it's linearly independent? Because we want to find the minimal object to build, minimal vector to build our space. Let's say we have one linearly dependent vector here. For example, what? For example, let's say we have -6, 0, 4, and 2. I claim that I don't need even to know the existence of this. Why? because if I look at the span, okay, if I look at the span of this 3 vector, I can build this vector already. Okay, so I can throw this away, such that I get a minimal vector to build my space. Does it make sense? Okay, because if this is minimal, if you throw any one of them away, you will build a smaller space. Okay, you will build a different space. But even if you throw this in, you still get the same space. Because how to obtain this vector here? You just take 2 multiplied by the last vector. Okay, no? So linearly independent means linearly independent and space together means you use the minimal vector to build the space you want. Okay, minimal vector. Does it make sense? Yeah. Okay. Build up spans mean build up. Last time I told you, right? Spans are fill out. You need to fill out the space. Okay, any question before we take a break? Let's take a break and then we do another example. Okay, let's break until 4:58. Okay. You want to ask question or?这个有。T 的，那个 standard matrix 怎么拿出来的？你还记得？And then 这一个就是 image of the moment， 因为刚才用。Yes, yes, yes, yes. 那你看是不是 image of 这些 T on top， 就是 E1 T 过后的那个。对，因为你是说为什么这个不是 M 乘 M 乘 N？你说这一个还是这一个？这一个是在指的一个。对，为什么要 M 乘 N？ 是因为我要这些 EI 出来，因为这些 EI 就是我在因为你的 T 是给我一个 Rn， 我给你的。所以我要 fit 进来的东西，不是一定是我在 M 还是 M？ 对，因为这个东西是什么？这边是 M， 这边是 N， 所以这边是变短，所以意思说你是放 Rn 进来，不是放 Rn， 但是你的 T 要吃掉 Rn， 你吃掉 Rn。
现在这个 x，给它要活在 R 里面，这个 matrix 变成 m 乘 n 的话，意思说它的 of row 是同的吧，不够长。我们在讨论这个的 size 的时候是什么？这一个的 size 应该是 m 乘，对，这个的 size 是 m 乘，但是这个 m 乘呢是在指这些东西 from 的一个 matrix，它不是在指这个。Okay, let's take another page. 袁若琪，哎，这个李长，哦，对，李长，刘浩奇，赵宏哲，赵宏哲，洪哲，赵宏哲，高子金，曹子金，sorry，陈俊，Amberly。Q 幺定啊，Q 幺烟Abdurrahman，OK，李思成，嘉宁，韦佳莹，岳阳，像宝俊豪，雷乱，林坤，李逸轩，萧亚轩，蔡碧，白无常，葛文业，郭汉宇，黄健，孙国东，张汉慈，张泰，钟义阳呢？张泰利，高子昭，金思豪，李云林，林灿许，刘涛，刘媛媛，杨，文瑞阳，王宏明，浩瀚，的徐泽瑞，于子洲，赵泽宇，Abdel Hibahir，okay. Benny here, Ismi, Benny Ismi, Shisa, okay. Nori Mohammed, also is here, right? Okay. Tanai, yeah. 这些，这首 OK。要问他只会吗？意见？Nicole，林子君，邱辉毅呢？邱辉毅，然后，sorry，慧月没有。高兴通，然后，Salami，这些 OK。高兴通，邱辉月，然后，高兴通，邱辉。
Hey, yeah, you can come here for.晚上7点啊，然后不会我们采访是吧？所以我就我今天上课再讲。哦，你可以 email 我啊，可以。不是有 email，我有 email 你的。上个星期，上个星期，那你可以找到，因为你其实蛮重要的，因为 email 是我们很多的。反而你找我应该是找不到，我不一定是在朋友，我就在 office hours 里面。对对对对对对对。OK，我就看到这个里面了，这个大概是 OK OK，但是你要常常看啊，因为我们是用 email，我放，而且晚上7点应该所有人都放工。有是刚好，我是因为我就去看过去。OK OK，so 你既能够跟得上，我们也是 breakfast，你这个是 very good，对的。因为是到就好会看，好会看，懂吗？大概应该是就是看啊，或者是个别的东西，是，对对对，但是很难，为什么？不了，不可能的，不了吧？嗯，在不同的 week 诶，是不同的 week，对呀，啊不了，不同的 week
啊，不同
啊，跟着 week，跟着 week，跟着 week，那边有 week 1、week 2、week 3啊，OK，也是，
它是两个三
这边没有15分钟的，我有那些 course info 里面都有写，
因
对啊
为
没有写多长
每，个 Friday 啦，
对，每个 Friday，OK，
去3个星期，
对，4个星期，
或者3次，
对对，
那个有的店是翻
很不对，
一到7
没错。So that's why 我们要有 quiz 来看你们有没有在读书，
这个学一点，
就可能3、4题吧，短短的15分钟的。Okay, so the quiz will be a short quiz, 15 minutes like that. To check your understanding whether you know some important calculation or not. Because final exam will be on everything. So if we don't test your whether you are studying or not, maybe you will very bad result in final. Okay, so every week we need to test whether you are keeping up, okay, to the content. Does it make sense? Yeah. Okay, it won't be like a tedious calculation. So basically, if you read the question, you know what to do, then you will get most of the mark. Okay, and then we will check whether you get the right solution or not. That's the other mark. Yeah. Okay. So next part. Find the basis, okay, for the column space and the row space. So there are 2 parts here. So let's solve it one by one. So let's recall again. What is a column space mean? So this is the span of what? Span of the column vectors. And then how about row space? Row space is a span of row vector. So can you see that where does a column vector live in? In this case here, right, 4 times 5, right? Okay, so column vector live in R4 or R5? Huh? 5 column or column vector, right? How many number? 4. How many number? 1, 2, 3, 4. All right, 4. Okay. So the size of column vector correspond to what? Number of row. Okay, number of row. Okay, a bit confusing. I chop into column, but the length is a number of row. But makes sense, right? Does it make sense? Yeah. Okay. How about row vector? You chop into rows. Okay, but how many number in the rows? Exactly the number of column. Okay, in this case here, it is R5. Okay or not? Okay, so you need to, how to say, look at the definition of column and row and then number of row and column to make sense of this. Okay, so let's look at the basis for column space. So, column space of A, so let's call it co A, right? Co A, not the notation, is span of what? So let's write down specifically 1 0 0 0 and then 0 1 0 0 and then -3 2 0 0 and then 5 -1 0 0 and then 0 0 1 0. Okay, so to find basis, right, you already know the span. You left with checking linearly independent. Okay, so what do you need to do for linearly independent? So you need to show that for C1 times this 1 0 0 plus C2 0 1 0 0 plus C3 times -3 2 0 0 times C4 plus 5 minus 1 0 0 0 0 1 such that they are all equal to 0 0. We only get the trivial solution. So in this case, what do you need to do? You do the row reduction on your augmented matrix. So you see, actually we are resembling the column vector into the matrix you had before. Okay, so why I bother writing down? Because I want to let you see the logic. Okay, I let you see the logic. Okay, to check that this column space is linearly independent, actually you just row reduce it. And just row reduce that row. Okay, you see, if you go through this process like the definition, right, you still get back this matrix. Okay, if you see here, again, did you see something or not? This matrix is already in a RREF form, right? Because you can see, you can find the pivot position here. Okay, you can find this 3 pivot position here. And then S3 and S4 are free. Okay, S3 and S4 are free. So how do you write this down? Maybe let's write down the general solution first in parametric form. What did you see? So 3 C3 on 3 minus 2 1 0 0 plus C4 of minus 5 1 and then 0 1 0. Okay, that's all. So is 0 trivial solution the only solution or not? Is 0 solution the only solution? No, right? Because you are free to choose this C3 and C4. That's why we call it a free variable here. Okay, in particular, what can you choose? Maybe you can choose 0 1. Okay, so this is a solution. This is a non-trivial solution to your linear system. Okay, so meaning what? Meaning meaning this span here, copy, paste. So this span here is not, sorry, not this span. This set, okay, we remove the span. This set of this 5 vector here is not linearly independent. But how? Can we create a linearly independent set or not? Huh? Can we create one? Out of these 5, can we create linearly independent set? What does this tell you? Actually, do you know how to read this solution here? Meaning what? You can get C1, okay, from C3 and C4. You can get C2 from C3 and C4. Or you can get C3 from C1 and C4. You can get C3 from C2 and C4. So, how do you reckon? What do you reckon? Can you cook out a linearly independent set from this 5 of them? Yeah. And on that. Well, I mean, yeah, how? So let's see if it's true or not. It says that C1, C3, and C5 have connection. Sorry, C1, C3, and C4. So look at the first one and the third one and the fifth one. Do they have a linear dependence or not? Have? Do they have a non-trivial linear dependence relation here? Huh? No. No, you sure? Yes. How do you show it? How do you show it? How do you show it? You take this tree and then solve it, row reduce, so that you get 3 pivot column. But you won't get 3 pivot column, right? You see, 1, 0, 0, -2, and 5, -1. You won't get 3 pivot column. But can you see a linear dependent relation or not? This is my question. Can you write something times V1, something times V3, something times V4, such that they add up to 0? We'll cook out one. So may try this. Yeah. Can easily see or not? So let's say I want to make this 2, 0. I only can borrow the 2 here. Because there's nothing to cancel this. And so if you want to make this 0, you need to at least 2 times this. Okay. And then what else? If you got 2 times this, you get -2. Okay, if you add them out, you get 0. But here become 10. Become 10, right? So 10 minus 3, you still have 7. Can you get rid of the 7? By what? -7 times the first factor. Okay, so we found a linearly dependent relation between these 3 actually. So we'll say that, not that. -7 times 1, 0, 0, 2 plus -2, 0, and then time 2 times. Okay, so there's a linear dependence relation between them. Okay, so similarly, this row reduced echelon form also suggests that these 3 have relation. Okay. Why I want to know that? I haven't finished yet. Yeah, I will finish it. Actually, you don't need to know this, but I want to show you it is that really exists a non-trivial linear dependent relation. Okay, but I will solve it. I will finish. Okay, so also you can see that this tree like C2, C3, C4, right? The corresponding vector also have linearly dependent relation. I challenge you, go back and try find it. Okay, can you cook up a non-trivial relation between these three? So the problem now is I want to find linearly independent set, right? So what do you reckon I need to do here? What do you reckon? I know 5 of these things will span my set. Okay? I want to make it linearly independent for everyone. So what do? I throw away the dependent guy. Correct or not? I throw away the guy. Huh? I throw away the dependent guy. Okay, because why? I can create the dependent guy from this independent guy. Does it make sense? Okay, so who we should throw away? Should we throw away? So who should we throw away? So the claim is, so this is my claim. Okay, B1. So following this reduced echelon form, right? We just keep the first one, second one, and the last one. Okay, so the claim is 1, 0, 0, 0. And then second one is 0, 1, 0, 0. And the last one is 0, 0. Okay, we'll span code A and they are linearly independent. They are linearly independent. Okay, so we just pick the pivot column. Okay, they will be linearly independent. Why? So think back again, because this is a claim, right? So I said it's span and linearly independent. So meaning, can we create C3? Can we create the third one? Okay, let's call this. Okay, let's fix our name for them. Easy to call them. So let's call the first one V1, V2, 3. Okay. So well, how do I create V3 and V4 from V1, V2, V5? We know that there's a relation between 1, 3, and 4. Okay, we also know a relation between 2, 3, and 4. So if we have V1 and V2, we should be able to create V4 and V5. This is the point. We do that. We do that. So this is just something to wonder about. So this is just why we can just pick these pivot column as our linearly independent set. Okay, why? Let me quickly say why. So for example, in this case here, if we know that we can solve V1 plus V3 C4, and then C2 V2 plus C. Sorry, maybe we use the other one D2 D3 plus D4. Yeah, okay. Can we find D3 and V4 or not? Can we find V3 and V4 given we know V1 and V2? Okay, and these two linear equation here. Back the equation. Can we find V3 and V4? Hang on. Can we express V3 and V4 in terms of V1 and V2? Hang on. express. So okay, so the question now is to, so let me pull out the exact question. So if we given V1 and V2, okay, and then we know these two linear system here, can you express V3, V4 in terms of V1, V2? Cannot. Can, right? Okay, so what do you do? So you can write this as V3 equals to something. Okay, so for example, from 1, maybe you can see that V3 equals to minus C1 V1 minus C4 V4 divided by C3. Okay, but procedure V4 from the second line. Okay, then you can express it in terms of V3 and V2. Then you are left with what? V3, V2, and V1. Okay, then you put all the V3 together. Then V3 will be equal to something V1. Okay, similarly for V4. Does it make sense? Okay. Okay. Any question? You can go ahead and try. Okay, go ahead and try for this case. Okay. But the method is you just keep the pivot column is enough. Okay. Keep the pivot column. Okay, notice that maybe some of you a bit dangerous. Some of you just pick the raw reduced guy. Actually, we are picking from the original set of vector. Okay, don't pick from the reduced guy. Yeah. Because you see the size is different. Hey, is it different? Okay, this case is the same. Okay, maybe row space is different. Okay, so later we'll see the row space case. Okay, so how about row space one? How about row space? Okay, now we will solve it for row space. So instead of seeing it like this, right, we should see the augmented matrix like this. Okay, so how to do this? So let's see. Let's do it for row space. So for second part, basis for space. Okay. Yeah, I'll tell you what I meant in a moment. Let's bring down my matrix. It's pretty big on this matrix. So 1, 0, minus 3, 5, 0, 0, 1, 2, minus 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Okay, so basis for row space means what? You chop your matrix horizontally. Okay, horizontally. So meaning what? You are looking at row A equals to the span of 1, 0, minus 5, sorry, 1, 0, minus 3, 5, 0, and then 0, 1, 2, minus 1, 0, and then 0, 0, 0, 0, 1, and 0, 0, 0, 0, 0. Basically, you can throw this 0 away. This is useless. Useless, right? You can't build any vector from the 0 vector other than itself. Okay, still remember last time we said about if you have a 0 vector in your set, then your set must be linearly dependent. Okay, so we can throw this 0 away actually. Okay. We can throw it first. Maybe just throw it first. Okay. Because anything add to the 0 vector still get vector. Okay, so now the problem is become whether you ask whether these 3 vectors are linearly independent. Is it independent? I think we should do row reduction. So let's do row reduction. Okay, we won't go through the explanation anymore. So let's quickly solve this augmented matrix. Okay, let's solve this. All right. So can you see that you can row reduce to these 3 pivots? Can quickly see? Okay. So you can cancel the third row using first and second row. Okay, use that as a pivot. And then the fourth row also use the first and second row to cancel out. Okay, and then this one you keep as a pivot. So what does it mean here? You just take this tree to be a linear independent set. Okay, and then span of this tree vector will be the what? Will be the basis. Okay, so basis for row A is exactly the first tree. Since what? Only two condition, only two condition here. Since the set is linearly independent, okay, because we solve the homogeneous linear system such that the trivial solution is the only solution, okay, because this one implies that C1 equal to C2 equal to C3 equal to 0, and the set span row A. This one is by definition. Okay, this one by definition. Okay, this is how we started with this row A. Okay. Any question? Okay. The main thing about basis is about linearly independent and the span. Linearly independent and span. So span is about consistent system, and then linearly independent is to solve the homogeneous linear system, such that 0 is the only solution. 0 solution. Any question? Any question? No question? Okay, if no question, let's continue first. Then maybe let's left the other one as a homework. And then here's the theorem. See, the pivot columns of a matrix A form a basis for the column space. Okay, this is what I show you this. If you want to find the basis of column A, go and look for the pivot column. Okay. So before jumping to dimension, right? This is what I hinted you a lot since last week. Let's do some summary on these null space and column space thing. Okay. So there's a very nice summary on null space and column space here. So this is a null space and column space for matrix A. This size is m times n. So you need to imagine. Once I tell you a matrix, you should imagine what's the size. Okay, m rows and n columns. So you can see that now A is a subspace of Rn because you are trying to multiply from the right. Okay, so it must be n times 1. Okay. And then column A is a subspace of Rmy because the m product is what? The m product is m times n. Okay, so that's why this guy here live in Rm. Okay, so this guy live in Rm, and then the null space live in. Okay. And so now A is defined by a vector that multiply to 0 from the right. And then column A is what? Is the one that you take linear combination of the column vector, okay, inside your A. Okay. And then what's the condition? Important condition. Let's see. It's easy to find the column space. Okay, this one. Okay, never mind. So jump to the fifth part here. So a typical vector in column of A has a property that the equation Ax equal to B is consistent. Okay, because you want to ask whether vector live inside a linear combination of these column vectors. So you need to solve that the system of linear equation is consistent. And then what else? What's important? Okay, I think the last 7 and 8 here is important. Okay, this one try and link back to a linear transformation already. Okay, let's look at 7 one. So now A is equal to 0, meaning what? only the zero vector will solve the AX equals 0. Okay, if and only if AX equals 0 has the only trivial solution. Okay, so this equal sign here means 0 can solve AX equals 0, and then everything that can solve AX equals 0 is just 0. There's only one thing. Okay, and then second, if this co-A span of the column, you can reach everything in Rn means what? Means that the equation, this matrix equation here has solution for every V in Rn. Okay? You can hit everything in Rn. So it's equal. And then second, now A equals 0 if and only if the linear transformation x to ax is 1 to 1. Remember, in the first start in the class, what did we say? If we want to check that the linear transformation x to ax is 1 to 1, what do we need to check? Ax equals 0 has only the trivial solution. Meaning what? Now A has only 0 solution. Okay, so Ax equals 0, we turn it into a language, call it null space. Okay. And then if column ARM is equal to M, so meaning we can solve it for every M. If and only if the linear transformation x to ax maps an onto Rn. Meaning you can hit everything inside the Rn. If you hit everything inside your core domain, means what? It is onto. Okay. Okay, so this is the language going between this subspaces and the linear transformation. Okay. Why go between? Because this is an if and only if. You can go back and forth one. So this is equivalent. Okay. So in algebra, right? We often turn a problem to the other equivalent problem. So you need to be how to say sensitive, okay, to this if and only if statement. Okay, if and only if meaning if you want to solve here on the right, we can solve it on the left. If we want to solve it on the left, we can solve it on the right. Can go back. Okay. Yeah. Okay, so this is the nice thing about linear algebra because we turn one question to the other question. Okay, because sometimes in the other setting it is easier to solve. Yeah, different cases, different settings. Okay. Any questions so far? So far, any question? No? Let's go to the next part. Okay, so next part will come to this dimension and rank. So before we talk about dimension and rank, we should talk about coordinates. Okay, so coordinates maybe you heard before is like the XYZ thingy, but now we will be more general to that. So suppose B is a basis for a subspace H, meaning what? This set of bases is linearly independent and span, okay, and span this H. So meaning what? If I take anything from the H, right, I can write it as a linear combination of B1 up to B. Okay, so meaning what? Everything in H is equals to C1 times V1 plus C2 times V2 plus up to CP plus BP. Okay, and then this is the minimal set because it's linearly independent. Okay, so next sentence is exactly what I said. Hx can be written uniquely, okay, as this linear combination. But I haven't shown you uniqueness, right? Maybe I'm not trying to show you, but actually it's unique. There's only one way. Unique means one way only. You cannot have different CI give you the same x1. Cannot. Okay, cannot. Okay, it's unique. Okay, so these CI are unique. And that's why we can just pick up the CI out. Okay, so the vector that built out by this coefficient is called the coordinates x relative to this basis here. Okay, so we don't need to record BI to BP. Why? Because the information is hidden inside this beta already. So what's important here is this CI, because this CI is the thing you change, okay, such that you change your x. B1 to BP, it won't change already. Okay, yeah, it won't change. Okay, no. Yeah. So the parameter here is CI, this coefficient. Once this coefficient change, it gives you another x. Okay, so each CI will correspond to a unit. Does it make sense? Does it make sense? Let's do one example. Okay, let's do examples. So, okay, so let's do examples. Right. So, very easy examples here. So let's say we have B1 equals to 1, 0, 0, 1, and then B2 equals to 1, 0, 1, 1. So I claim that these are the bases for R2. These are the bases for R2. So to see that they are the basis for R2, right? Okay, this part is pretty important. I want to tell you because we're gonna put into exam this part. So these two are bases for R2. Why? So you need to answer two questions, right? Linearly independent and span. Okay, linearly independent and span. So can you see that why are they linearly independent and span? So maybe we just look at them one by one. So let's look at it one by one. So check. First, check that they are bases. Okay, first check that there are bases for R2. So for the first one, we have 1, 0, 0, 1. Okay. So why is it spanning? So first part, B1 span R2. Okay, meaning what? For everything, okay, inside the thing that you want to span here. So meaning for every x1 in R2. Can you express it as a linear combination of these two or not? Can or not? What's the coefficient you can pick here? What do you reckon? What are the coefficient you can pick here? X and Y. So this is the span part. How about linearly independent? You need to row reduce this matrix, right? So this is already row reduced. And then the only solution to the homogeneous linear system is 0. Okay, so since C1 equals C2 0. Only, okay, since only C1 equals C2 equals 0, solve it. So the linear dependent vector equation, the set B1 is linearly independent. Okay, similarly for the second one, I claim that it's a basis, right? So we should show that it is a basis also. So how to show span? What do you think? Yeah, I think linearly independent is easy to see, right? Okay, actually, you found two pivot already. And then if you go further row reduce this, right, you can make this 0. Right, row 1 minus row 2. Okay, so actually second part is similar. How about first part? Can you find coefficient to express any x1 in terms of 1, 0 and 1, 1? A little bit harder, huh? A little bit harder, right? But what should you do if you learn linear algebra properly? What should you do here? You should go and, if you want to find C1, C2, right? You should go and row reduce your augmented matrix. Okay. But I claim that it's not too hard to do inspection. It's still not too hard to do inspection. Can you quickly do some inspection? What you need to put here? Obviously, you see, okay, I can teach you some way to do quick inspection here. You see, you want to have y on the second spot, right? But this term here couldn't produce anything for second spot because second spot is 0. No matter what you multiply in, you get 0. So the only place you can get y is from the second one. So you must at least have y here. Let's say you already have y here already, right? But in compensate, right, you have a y on the first spot, but you don't have y on the first spot here. Instead, you have a x. But what can you do here? X minus y. Good, very good. So you should put a x minus y. In case you are not happy, go and do this row reduction, you get the same answer. Right or not? What do you do? Row 1 minus row 2, row 1 minus row 2, x minus y. Okay, yeah. So everything works one. Okay, math is like that. No matter you attack from which direction, it must be the same answer. Okay, this is the beautiful of math. Okay, no matter where you attack. Okay, so good. So these are basics already. So what's my question here? So my question here is, now the question is, try and write, what's the language? Okay, the coordinate vector. Try to write the coordinate vector. Or let's say, let's pick 2 and minus 3. Okay, relative to beta 1 and beta 2. Okay, so for the sake, for you, I will copy out again 1 0 for the sake of doing. Okay, I give you 2 minutes. Try and work this out. You can check with your friend. Okay, try and write the coordinate vector relative to b1 and b2. Okay, so meaning you need to get the coefficient out when you express in terms of p basis. Okay, so can you tell me what's the coefficient you should put there? 2 and minus 3 for the first one. How about second one? 5 and minus 3. Okay. So in this case here, what can you see? The coordinate vector correspond to beta 1 is what? 2 and minus 3. And then the coordinate vector correspond to beta 2 is 5 and minus 3. Okay, so to get this, actually we have worked out the general solution right just now. X minus y and y. Okay, x minus y is 5, y is minus 3. And then here is just using x and y. Actually, just now we worked out a general solution already. So what do you think of this? How do you think of this 2 vector here? One vector corresponds to 2 coordinate vector, meaning what? It's like an address change. Change of address. Address. You know what's address? Yeah. Okay. It's the same guy. It's the same guy. Okay, but live in a different. It's the same space, but a different address. We change the road name, for example. Maybe. Okay, we change the road name. They give you the same space, but we describe the space using different bases. And then this vector will live as a different. How say? As a different vector. Yeah. So you can see that every vector in Rn has this is equals to x coordinate vector if the basis we consider is a standard basis. Okay, if it's not standard basis, then this coordinate vector will change. Okay, yeah. Does it make sense? Any question? Any questions so far? Okay, we're gonna define new stuff using this coordinate system. see. Hey, what are we doing? Okay. Let's see, should we get something here? Okay. I think this one is quite straightforward. Right? So verify that x is in the span, and then find the coordinate x. Are you guys okay with this? Should we go through this together, or you can try yourself? You know what to do with this? Check span, solve the linear system, and then get the coordinate vector. Get the coordinate vector means what? You collect the coefficient. So how many coefficient here? Maybe I test you first, I see if you know. So if I write x, okay, as this span of v1, not span of v1, v2, right? This basis here. Okay, so what's the size? What do you think? What's the size? How many coefficient you get? 2, right? Okay, it's 2. Where do you get the 2 from? You need to express your x of c1 v1 plus c2 v2. Okay, so once you solve this, you will get the coordinate vector. Okay. Can try also. You know what to do. Okay, you should know what to do and then go back and try and calculate. I'll give you answer. We can check. Okay, I leave it for you. Okay, so if you still don't understand, you can ask again. We will do it together next. All right. So the point is, okay, the point is what? The point is we can define this dimension of a non-zero subspace, okay, denoted by dimension h, is the number of vector in any basis. The dimension of a zero subspace is 0. Okay, we won't say 1. It's 0. Okay, so the dimension is defined to be the number, okay, the number in any basis of it. And then rank of a matrix is defined to be the dimension of co-A. Okay, so I will say that rank A is equals to the dimension of co. Okay, so what time is it? 5:45. Maybe let's try do one more. And then almost break. So I'll try and determine the rank of this matrix here. So how to determine the rank of this matrix? So you need to figure out the basis of co-A first. Okay, how to figure out the basis of co-A? Maybe I don't make you work. I tell you what's the solution. See if you can read from the solution or not. So let's say we know that we can reduce it to this guy, the echelon form. Okay, go back, you can fill it in. So from here, what can you see? Just now, what do we say? Where do we get the basis from? Pivot column. So where's the pivot column here? First one, second one, and the fourth one. No third one, no? Okay, right, because we already have a pivot in that row. Okay, so meaning what? This pivot columns will form a basis of column space. So how many of them? 3 of them. Okay, the dimension is 3. So implies that the rank is 3. Okay, so since there are 3 pivots, so the rank of A is 3. Okay, okay. So again, I want to warn you, don't if you want to pick the basis, right, don't pick from the reduced one. You need to pick from the original one. Okay, because they might not be the same. So I have a warning for you here. So there's a warning here. Co A is not equals to the co of reduce A. Not necessarily. Not necessary, because how do you get this row reduce A? You are doing row operation. And row operation maybe doesn't respect the linear combination. So since there are 3 pivot, rank A is 3. How to get the 3 bases here? You should get from the first one, second one, and the fifth one. So this is the 3 vector, okay, inside your rank, inside your bases. Okay. Okay, maybe we mention some result first, and then we will repeat the result next time. So one result is if A is an m times n matrix, then your dimension of the column of A, so which is rank A, plus the dimension of now A, okay, it will complete to this n here, number of column. Okay. And then rank A is equal to rank of A. Rank of AT is actually the dimension of row space. Dimension of row space, because row become column, and then you ask about that dimension. Well, actually, this is equals to the dimension of row A. Okay. Yeah, so this is a rank theorem. Maybe it's important. If you want, you can memorize. Okay, maybe we can stop here. Tomorrow we can continue. Okay, we'll see you on Friday. On Friday. Okay. Yeah. Oh, Cho, wait.